Here's another kind of tension problem. Let's imagine we have a mass m1 sitting on a horizontal surface, and there is a string coming from m1 and going over a pulley that then comes down, suspending m2 below it. Okay, well, let's try and solve this one. Let's assume that, just for the sake of argument now, let's assume there's no friction between m1 and the surface, and let's assume that the pulley is massless and frictionless. So what does that mean? The string can pull over the pulley, and there's no resistance on the string from the pulley. What that means then is that whatever the tension is up here, it's the same tension as down here. If the pulley actually had mass and was difficult to rotate, or if there was some friction in the pulley, then these tensions could actually be different, and we'll see situations like that later on. But for this problem, we'll assume that the tensions are the same. Again, we're going to assume that the string does not stretch, so whatever amount m2 comes down will be the same amount as m1 goes over, which basically tells us what? The accelerations will have the same magnitude. I didn't say will be the same because let's keep in mind that m2 will be accelerating downwards while m1 will be accelerating to the right. So while the directions are not the same, the magnitudes are the same, and that's going to be very, very important for us. We could break this down into x and y parts, but this is going to be funny because motion of m2 will be in the y direction, motion of m1 will be in the x direction. But motion of m1 in x corresponds to motion of m2 in y. So let's just look at the magnitudes of the motions and not worry about the fact that they're actually perpendicular to each other. We don't have to take that into account because we know that the overall magnitude of the acceleration is the same. So let's look at the equation of motion, in other words, Newton's second law. Let's apply Newton's second law to m1. So first of all, what are the forces acting on m1? Well, we've got this tension that's pulling to the right, some magnitude t. We know it's got a weight, m1g, and then we'll have a normal force. Again, it's going to be equal to the weight, so this will be m1g. And again, we call that F1, and F normal 1 and weight 1. All right, so what's the equation of motion for mass 1? Well, the force, the net force on mass 1 will be T, and that's going to equal m1a. All right, what about the forces on m2? Well, in that case, we've got a weight of m2 pulling down. So weight 2, we know that's going to be m2g. We have a tension pulling up, and those are all the forces. So those are all the forces that are acting on T2. So what's the equation of motion for T2? The net force on T2 will be, how do we want to do this? Because if a positive motion for m1 is this way, then a positive motion for m2 would be down. So while we said that motion to the right for m1 was positive, let's say that motion down for m2 is positive. Or else we'll have to have one acceleration positive and one acceleration negative. Okay, that just makes it harder. So we'll assume that basically motion this way is positive. So what are the positive forces on, or what are the forces on mass 2 with downward is positive? Well, that'll be weight 2, so m2g. And then minus t. And that must equal m2a. All right, very good. Again, we've got two unknowns here, t, the tension, and a, the acceleration. But luckily we've got two equations with two unknowns, so yes, we can still solve it. And again, we're not worried about this. We've already put the forces in. So what do we have? We've got t equals m1a, and m2g minus t equals m2. Well, we've already solved for t, so let's take this and put it in over there for t and see what we get. We get m2g minus t, and t is m1a, equals m2a. Well, let's solve for a. Let's bring this over here. We can factor out an a and divide by m1 plus m2. And what do we get? We get a is equal to, dividing by m1 plus m2, we get m2 over m1 plus m2 times g, and there is a. Now let's take that and stick that in here to find t. So what do we have? T equals m1 times a. Well, that's going to be m1, m2 over m1 plus m2 times g. All right. Very interesting. Let's take a look at both of these results in an extreme and see what we get. Well, first, let's imagine that m2 much larger than m1. So with m2 much larger than m1. We have m2 over here pulling down, m1 up here. Think about what would you expect if you have a very large mass here attached to a much smaller mass up here. What do you think is going to happen? Well, let's see if that's what we get. All right, if m2 is much larger than m1, m1 plus m2 is basically m2. And we get m2 over m2, which is 1, and we get the acceleration is basically g. Okay, well that makes sense. That makes sense because if m2 is much larger than m1, m1 is not going to have much of an effect on m2, and it's just going to fall down in free fall, and that's what we get. The acceleration is g. Okay, that makes sense. What do we get for the tension? Well, if we have m1 plus m2 basically equal to m2, m1 times m2 divided by m2, the m2's cancel, and we get m1g. We get the tension is m1g, which also makes sense because we know m1 is going to be accelerating at g, so what force must be acting as the tension to accelerate m1 at g? It must be m1g. All right, well that makes perfect sense as well. Very good. What about for m2 much less than m1? All right, then what do we get? Well, if m2 is much less than m1, m1 plus m2 will be basically m1. m2 over m1 will be a very small number. So the acceleration is going to be a small number times g. Well, all right, let's just write that down. So a is small. Basically going to 0. What tension do we get? Well, if m2 is much less than m1, then m1 plus m2 will basically be m1. The m1's cancel, and we get the tension is m2g. All right, well, let's think about that. We've got a very large mass up here and a smaller mass extending off of here and hanging by it. Well, what do we expect the acceleration to be? Well, we've got this little tiny mass here and a great big one up here. We're going to expect that that force is going to accelerate m1 just a tiny bit. So m2 is going to accelerate downward very slowly. That's what we find, a small acceleration. What kind of a tension do we expect? Well, because m2 is not accelerating very rapidly, it's basically just hanging there. And so the tension is nothing more than the weight of m2. m2 is basically hanging on a string that's got its weight, so basically m2 is not moving a lot, and that's exactly what we find. All right, again, very interesting, and that makes complete sense. What about for equal masses? For m2 equal to m1, what do we get? Well, if m2 equals m1, m1 plus m2 will be 2 times m2. m2 over 2 times m2, the m2's cancel, and we get 1/2. We get an acceleration of 1/2 g. And what about the tension? Well, m1 plus m2 will be 2 times m1. m1 over 2 times m1 will be 1/2. We'll get m2 over 2 times g. So T equals m2 over 2 times g. Well, what is this telling us? Well, in this case, if we've got equal masses with only a force of m2g trying to accelerate it, but we've got a force of m2g acting on a mass basically of 2 times m2g, it's only going to accelerate it half of g. And that's exactly what we find. The acceleration is 1/2 g. Because the amount of force acting basically to accelerate both is only half the force that would be needed to accelerate both of them at g. And then what's the tension? Well, what we find is that the tension is half as big, and it cancels the weight of m2g, and so we only end up with basically the tension being half the weight, so that's canceling out half of the weight that's acting down, so the net force acting on m2 is just half of its weight, so it only accelerates at half of g. And that makes sense. All right, very, very good. Let's take a look at another one.